Welcome back. So, we were discussing an adiabatic turbine and an adiabatic compressor. We looked at the first law for both of them and we looked at their HS diagram. Now, we look at another adiabatic open system, and this is a nozzle. A nozzle is not a work transfer device, and what is expected from a nozzle is that we increase the velocity of the fluid, and this is a device which is used mostly in turbines and even elsewhere. So, what happens is if we write down the first law for a nozzle in full, let us just write down the steady state first law, which is q dot minus w dot s is equal to m dot h e minus h I plus V e squared minus V I squared by 2 plus G Z e minus Z I. The nozzle is expected to be an adiabatic device. So, we say this is nearly equal to 0, the q dot. We are not extracting or inputting any work into the system. So, this is equal to 0. Typically, we do not expect any change in the potential energy of such a system, and this is a reasonably good assumption to put this as equal to 0. So, what finally remains is that there is a significant delta H between the inlet and exit of the nozzle, and as a result we get an increase in the velocity of the fluid at the exit. So, we have finally that H e minus H I plus V e squared by 2 minus V I squared by 2 is equal to 0. It can also be written as H e plus V e squared by 2 is equal to H I plus V I squared by 2. Now, we just depict the nozzle as it is typically shown in an open system manner. We do not draw a trapezoid here, but the fact is that we go from a higher pressure to a lower pressure. The trapezoid we have already used for a turbine, but this is the inlet. So, we just draw I here. We go from a higher pressure and a higher enthalpy to the exit here, and this is normally how we show it here, and what we really get out is V e. So, we can assume negligible inlet velocity, even if it is there, it is much smaller than V e. So, this is really what we are interested in, V e, and typically this is what is written. So, for this P e is much lesser than P I, that is the exit pressure is less than the inlet pressure, H e is less than H I, and V e is definitely much greater than V I, and we have assumed of course that W dot S is equal to 0 and it is reasonably adiabatic. Q dot is 0. We have also said delta P e is nearly 0. So, we realize that in this case what has happened is, as far as the HS diagram goes, it would be the same as that of a turbine, because there is a significant drop in H, which instead of the work output has resulted in an increase in the velocity, and the second law is going to be the same as that for a turbine, in the sense that we will have the exit entropy S e minus S I should be equal to S dot P, which is a quantity greater than 0. So, S e would be greater than S I, and hence one can draw the HS diagram as follows. This is H and S. This is the inlet isobar P I. This is the inlet state. This is the exit isobar P E, and ideally we would have come from I to E star. So, we would have gotten S E star is equal to S I. We had P I which is greater than P E in this case, and we had H I greater than H E in this case, and if the process is not ideal and if there is entropy production, one expects to move in this fashion towards increasing entropy. This is an adiabatic case, and we would have gotten E here such that SE is greater than SI, or SE, I should say greater than or equal to here, and SE is definitely greater than or equal to SE star, which means that the first law we had written, HE plus VE squared by 2, which is equal to HI plus VI squared by 2, we can of course write even for the ideal process the same, HE star plus VE star squared by 2 is equal to HI plus VI squared by 2. This is the first law, it does not change, but since we see that just as in a turbine there is a lesser delta H now actual, and compared to the ideal delta H, and since HE star is a quantity which is less than or equal to HE, and hence this implies that VE star is a quantity which is greater than or equal to VE. We have VE star greater than VE. This is what we expect. The nozzle is used to accelerate the fluid to a higher velocity, and what we get or what we are expected to get ideally, that is VE star, is higher than VE, which is what we get actually. So, because the nozzle has not performed to what we expect because of irreversibilities and because it is not ideal, we have VE star, that is the ideal velocity obtained at the exit is greater than the actual velocity at the exit. Now, because of this we can of course define an efficiency for a nozzle similarly as what we had done for a turbine and compressor, and that is what we can write down here. We will call it the isentropic efficiency of the nozzle. Since we are basing it exactly on the same principle, we say that what we would have got ideally is VE star by 2. This is the ideal expected output from the nozzle. What we get actually, so this is ideal, this is actual, the actual is VE square by 2. VE squared by 2 is a smaller quantity, and just as in a turbine we will define isentropic efficiency of the nozzle, which we can write as VE squared by 2, that is what we get actually upon VE squared by 2 or VE star by 2. This is the ideal kinetic energy output from the nozzle, and this number, as you can see, because VE star squared by 2 is greater than or equal to the actual VE squared by 2, this number will be less than or equal to 1 as expected, and this is what we call as the isentropic efficiency of the nozzle. Thank you.